Welcome back. Problem 3-17. This problem is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by R.C. Hibbeler. So statement is a tension test was performed on a magnesium alloy specimen having a diameter of 0.5 inch and gauge length 2 inch. The resulting stress strain diagram is shown in figure. Determine the approximate modulus of elasticity and the yield strength of the alloy using 0.2% strain offset method. So you can see this is a stress strain diagram for magnesium alloy. Initial diameter was 0.5 inch and the gauge length is 2 inch. So gauge length is the length over which we perform this tensile test. Okay, so this is the resultant stress strain diagram. So you have to find the modulus of elasticity, and then using 2.2% strain offset method, you have to determine the yield strength. So let's start with the solution. So what we will do is that we will first find modulus of elasticity, and this modulus of elasticity E can be found by using this stress strain curve. So you can see this is the proportional limit or elastic limit. So the slope of this curve will give you the modulus of elasticity. So E will be equal to, here you can see if I take this point, so at this point you have stress which is equal to 13 ksi and the strain will be 0.02. So I will take 13 if you take the stress, so 13 minus if you this 0 will be equal to the strain 0.002 minus original strain, which is again 0. This will give you the modulus of elasticity. So you will get 13 divided by 0.002. And you will get this modulus of elasticity E approximate will be equal to 6.50 into 10 raised to the power 3 ksi. So this is how we can find the modulus of elasticity using stress strain curve. Now we'll move towards second part, and second part states that to find the yield strength. So how you will find this yield strength? It is given 0.2% strain. Clear? So 0.2% strain is actually 0.2 divided by 100, and that is equal to 0.002 strain. So at 0.2 strain, what we are going to do is that we will draw a line that is parallel to initial line, this stress strain curve line, this line. You can see this, we will draw a parallel line. And I will write the remaining thing, the intersection point between stress strain diagram and the straight line drawn parallel to the initial portion of stress strain diagram from offset strain of 0.002 inch per inch is the yield strength of the alloy. So you can see that this is the original stress strain diagram line, and this is when the stress strain line when you take 0.002 offset. So this is the intersection point. Now at this intersection point, if I proceed it to the horizontally, and it will cross this vertical line, so this point will give you the yield strength. This is what I mean. So you can see yield strength will be equal to, let me take this line, so this will be approximately equal to 25.9 ksi. So yield strength will be equal to 25.9 ksi. And this is the answer of our second part. So this is yield strength sigma y. Clear? And that was all about this problem 3-17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos among your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 3-13 that is taken from chapter number 3, Mechanical Properties of Material, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is a bar having length of 5 inch and cross-sectional area of 0.7 square inch is subjected to an axial force of 8,000 pounds. If bar stretches 0.02 inch, determine the modulus of elasticity of the material. The material has linear elastic behavior. So you can see this is the bar having 5-inch length, clear, and there is axial load of 8,000 pounds. And due to this load, it stretches means change in length will be 0.002. So you have to determine the modulus of elasticity. First, we will write the given data. Bar length is 5 inch, cross-sectional area is 0.7, axial force is 8,000 pound, and the change in length or bar stretch is 0.002 inch. The material behave elastically. Clear? And we have to determine the modulus of elasticity. So let's start with the solution. So as we know that modulus of elasticity, which is equal to E, elasticity, which is equal to E, and that E is equal to stress divided by strain. So we do not know stress and strain. So first we will define or we will determine stress. So stress here is equal to axial load divided by the area over which it acts. So axial load is 8,000 pounds. So I will write 8,000 pounds and area is 0.7 inch square inch. So when you divide it, so you will get 11.43 into 10 raised to power 3 pounds per square inch. Or in term of KSI, it will be 11.43 KSI. KSI is kilopound per square inch. So you will get 11.43 KSI. Now what we will do is that in second step, we are going to find strain. And you know that strain is equal to change in length divided by original length. Let me write original length, L. So change in length or stretch is given as 0.002 inch, 0.002 inch, and original length of this bar is 5 inch. So inch divided by inch, and you will get 0.000400, and it will be inch by inch or unitless because they will cut each other. Now modulus of elasticity, E will be equal to stress over strain. So you have both the values. Stress is 11.43 KSI and strain is 0.000400 inch per inch. So you will get the value of modulus of elasticity will be 28.6 into 10 raised to power 3 KSI, which is the answer of our this question. So this is the modulus of elasticity for the given load and the cross-sectional area for the material. And that was all about this problem 3-13. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 3-18 that is taken from chapter number 3, Mechanical Properties of Materials. And book name is Mechanics of Material by R.C. Hibbeler. So statement is a tension test was performed on a magnesium alloy specimen having 0.5 inch diameter and gauge length of 2 inch. The resulting stress strain diagram is shown in figure. If the specimen is stressed to 30 KSI and unloaded, determine the permanent elongation in the specimen. So you can see this is stress strain diagram for magnesium alloy, clear, and we have to find the permanent elongation, clear, if it is stressed to 30 KSI and then unloaded. So let's start with the solution. So first step is that we will find the modulus of elasticity, E approximate, using this stress strain diagram. So how you will find this? So you can see this is the stress strain diagram and this is elastic limit. So in this elastic limit, if you look at this point, so this is the stress, let this is 13 and here it is 0. So 13 minus 0 divided by strain. At this point, strain is 0.002. 0.002 minus original strain is again 0. So when you solve this, you will get modulus of elasticity is equal to 6.50 into 10 raised to power 3 KSI. Okay. Now we have find this. You can see that it is given that for 30 kilonewton, 30 KSI load. So it is loaded to 30 KSI. So again, at this load, the strain will be 0.0078. And after it is unloaded, it comes back, but it will not be it will not come to its original position and it will have certain strain. So how you will find that strain? That is what we call permanent elongation. So let me write it. Permanent elongation. So from stress strain diagram, from stress strain diagram, the strain recovered is along the straight line BC, which is parallel to straight line OA. We can find this permanent strain. How you will find this? Let this is point O, this is A, and this is B. Clear? So permanent deformation will be equal to, you can see at point B we have 0.0, which is total strain, so which is 0.0078. So again, when you release this load of 30 KSI, clear, it will not come back to original position, but it will have certain strain. So how we'll find that certain strain? That can be obtained by using the load 30 KSI. So 30 into 10 raised to power 3 over the modulus of elasticity, which is 6.50 into 10 raised to power 3. Clear? And that will give you the permanent strain in that object, and that is 0.00318 inch per inch. So what does it mean? It means that let this is 0.00318. So after removing this 30 KSI load, it will come back to this, and you can see this line. This is point C. So this line BC is parallel to the initial line of stress strain diagram, and there will be a permanent strain will remain in this material. So I will also write it over here that this will be the permanent strain, epsilon P. This will be epsilon P. Now you can see that we know that strain is equal to change in length divided by original length. So for permanent strain, this permanent strain will be equal to permanent length divided by original length. So we are interested to find out the permanent elongation. So permanent elongation is equal to permanent strain into original length. So permanent strain is 0.00318 and original length or gauge length is 2 inch. So we will multiply this 2 and you will get the permanent elongation, and that permanent elongation will be 0.00637 inch, which is the answer of our this question. So this will be the permanent elongation in the originally gauge length of 2 inch magnesium alloy specimen. And that was all about this problem 3-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. And if you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 3-21. This problem is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by R.C. Hibbeler. Statement is the two bars are made of polystyrene, which has the stress strain diagram shown. If the cross-sectional area of bar AB is 1.5 square inch and BC is 4 square inch, determine the largest force P that can be supported before any member ruptures. Assume the buckling does not occur.
So you can see these are two bars. This is bar BC and this is bar AB. At this point we have pin supported and C is also pin supported. Here we have a P load. The stress strain diagram for this two bars are given. For the tension, for member tension, this will be the stress strain curve, and for the member which are in compression will be follow this stress strain curve. So you have to find the largest load P that can be applied before any member rupture. So let's start with the solution. So what will be the first step is that we will use method of joint at B in order to find the forces in CB and AB. So you can see due to this load P, clear this bar CB will be in tension and this AB will in compression. Clear? So while taking the method of joint at B, so this bar CB will exert a force on B at this direction. Similarly, the bar AB will exert a force on at point B in this direction. So let me draw the free body diagram. This is point B, clear, where we have a load P that is acting downward, clear. The force that member CB exert on point B will be this FCB, and the load that this member AB act on point B will be this one, and this is an inclined force. This is FAB. Now you can see the ratio of their side. This is 3 feet, this is 5 feet. So horizontal will be 3 feet, vertical will be horizontal is 4 feet and vertical is 3 feet. So this hypotenuse will be 5 feet, and we can find its horizontal and vertical component by using equation of equilibrium. So what will be the first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So one force which is P is acting downward, so minus P plus the vertical component of this force. So it have two force, one is this and other one is this. So this component will be, if you take this is theta, clear. So let this is theta. So what will be sine theta? So sine theta will be equal to 3 over 5. And what will be cos theta? So cos theta is equal to 4 over 5 base by hypotenuse. So vertical component will be FAB sine theta will be equal to 0. So minus P plus FAB and sine theta is equal to 3 over 5 is equal to 0. So it means that 3 over 5 FAB is equal to P. And from here we will get FAB will be equal to 1.6667 times P. Now we will apply another equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So FCB is acting in opposite direction, so I will write FBC, clear. The horizontal component of this will be like this, and this will be equal to FAB cos of theta. Let me write it plus FAB cos of theta is 4 by 5, clear, is equal to 0. So from here you will get FBC is equal to 4 over 5 time FAB. Now you know that FAB is 1.6667 times P. So you can put the value and at the end you will get this FBC, and FBC will comes out to be 1.333 times P. Now you have both FAB and FBC. So what we will do is that we will first assuming failure of bar BC. From this figure, you can see that due to this load, the bar BC will be in tension. So you will use this stress strain diagram. So from this stress strain diagram, rupture stress due to tensile loads comes out to be 5. Clear? So we can write 5 KSI. We know that stress is equal to force per unit area. So for this member BC, we will have rupture due to tension will be equal to FBC divided by area of BC. So what we have is 5 KSI is equal to FBC divided by area of BC is 4 square inch. So 4. So from here you will get this FBC will be equal to 20 kips. Now you have this FBC is 20 kips. So you can see you can put it in this equation. So what you will get is that 20 is equal to 1.333 times P. So what you will get is that P load due to this member BC, and this P loads comes out to be 15 kips. So this is one load that is due to the member BC. Now what we will do is that we will use assuming failure of bar BC, AB. You can see that due to this load, this bar AB is in compression, clear? So we will use this rupture stress due to compression. So I will write rupture due to compression is equal to 25 KSI from stress strain diagram, and this rupture due to compression is equal to FAB divided by area of AB. So from here FAB will be equal to rupture due to compression into area of AB. So you have both the value 25 multiplied by area of AB is 1.5 square inch. So 1.5, and you will get this force in member AB. So this force in member AB comes out to be 37.5 kip. Now this is the force FAB. So you can just put it in this equation. FAB is 1.66 times FAB is equal to 1.6667 times P. So from here P will be equal to FAB divided by 1.6667. So put the value 37.5 divided by 1.6667, and you will get this P will be equal to 22.5 kips. So this is the load P that is due to member AB. Now we have two value. One is this one, another one is this one. So we will choose the largest load. We will choose the largest load that can be applied on this system will be P will be equal to 15 kips, because this will be the safer load. So we will choose smaller one, and that is the largest load that can be applied on the system. So this was all about this problem 3-21. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 3-22 that is taken from chapter number 3, Mechanical Properties of Materials, and book name is Mechanics of Material by R.C. Hibbeler. So statement is two bars are made of polystyrene which has the stress strain diagram shown. Determine the cross-sectional area of each bar so that bars rupture simultaneously when load P is 3 kips is applied. Assume that buckling does not occur. So you can see this is bar BC and this is bar AB that is acted upon by load of P, which is 3 kips. And there is stress strain diagram for the bar in tension is this one, and for the bar which is in compression is this one. And it is given that to find the cross-sectional area of this BC and this cross-sectional of area of this AB of the bar, so that these bar rupture simultaneously. So let's start with the solution. Now due to this load, you can see this bar BC will be in tension and this bar AB will be in compression. So this bar CB will exert a force on point B in this direction, and this bar will exert a force on point B will be in this direction. So we will using method of joint at point B, method of joint at point B, we will find these forces in the member. So let this is point B, clear. So at point B we have P load, which is 3 kips, that is downward. So the force exerted by this bar CB on point B will be FCB, clear. Similarly, the force that bar AB will exert on point B will be equal to FAB. Now, if you look at this FAB will be at certain angle theta, clear. And you can see that this height is 3 feet and this length is 4 feet. So this is 4 feet. This height is 3 feet. 3 feet. So this hypotenuse will be 5 feet. So this will be there. This will be the ratio of their sides. So if I take sine theta, so sine theta will be equal to 3 over 5. If I take cos theta, so cos theta will be 4 by 5. And this force will have two components. One along x-axis, clear, in this direction. Another one will be in y direction. So this component will be FAB sine theta, and this component will be FAB cos theta. Now we will apply equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is positive. So 3 kips, which is downward, so minus 3 plus this vertical component, which is FAB sine theta, is equal to 0. So it means that FAB sine theta is equal to 3 over 5 is equal to 3. Clear? And we will get this FAB will be equal to 5 kip. Now we'll find this FAC by using another equation of equilibrium that sum of all forces along x direction must be equal to 0 and force towards right will be taken as positive. So you can see FAB is in positive direction. So FAB cos of theta minus this FCB, which is in opposite direction, is equal to 0. And you can see that cos theta is equal to 4 over 5. So 4 over 5 minus is equal to FCB, and FAB is 5. So 5 multiplied by 4 over 5 will give you FCB. And you can see that FCB will be equal to 4 kips. Now you have both forces in the member. In member AB it is 5 kips, and in member CB it is in 4 kips. So for member ABC, you can see due to the load this member BC will be in tension. So for rupture we will take the maximum load, stress will be 5 KSI. So we will use rupture for tensile is 5 KSI, and from here we know that rupture for tensile is equal to force BC divided by area of BC. So we are interested to find out the area. So area of BC will be equal to rupture stress for tensile divided by force BC. So 5 KSI divided by FCB is 4. So we will correct it. This is 4. So when you calculate it, area of BC will come out to be 0.8 square inch. Similarly, we will find for member AB. For member AB. So you can see that this member AB will be in compression. Clear? So we will use this stress strain diagram, and sigma rupture for compression here is 25 ksi. So we will write 25 ksi. So sigma rupture under compression is equal to 25 ksi, and we know that sigma rupture for compression is equal to FAB divided by area of AB. So from here, area of AB will be equal to rupture stress under compression divided by FAB. So you can put the value 25 divided by FAB is 5. So I think we have made a mistake over here. You have to correct it. This area of AB will be equal to FAB divided by sigma RC. So FAB is 5 divided by 25 will be area of AB, and when you calculate it, this area of AB will come out to be 0.2 square inch. Similarly, you can also rectify it. The mistake which I have done earlier is this FBC divided by sigma R due to tension. So FBC was 4 divided by 5. So 4 divided by 5 will give you 0.8 square inch. And so this is the area of bar BC, and this is the area of bar AB, which will rupture simultaneously under a given load of P is equal to 3 kips. And that was all about this problem 3-22. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 3-13 that is taken from chapter number 3, Mechanical Properties of Material, and the book name is Mechanics of Material by R.C. Hibbeler. So statement is a bar having length of 5 inch and cross-sectional area of 0.7 square inch is subjected to an axial force of 8,000 pound. If bar stretches 0.02 inch, determine the modulus of elasticity of the material. The material has linear elastic behavior. So you can see this is the bar having 5 inch length, clear, and there is an axial load of 8,000 pound. And due to this load, it stretches, means change in length will be 0.002. So you have to determine the modulus of elasticity. First, we will write the given data. Bar length is 5 inch, cross-sectional area is 0.7, axial force is 8,000 pound, and the change in length or bar stretch is 0.002 inch. The material behave elastically. Clear? And we have to determine the modulus of elasticity. So let's start with the solution. So as we know that modulus of elasticity, which is equal to E, elasticity which is equal to E, and that E is equal to stress divided by strain. So we do not know stress and strain. So first we will define, or we will determine stress. So stress here is equal to axial load divided by the area over which it acts. So axial load is 8,000 pounds. So I will write 8,000 pounds, and area is 0.7 inch square inch. So when you divide it, so you will get 11.43 into 10 raised to power 3 pounds per square inch, or in term of KSI it will be 11.43 KSI. KSI is kilopound per square inch. So you will get 11.43 KSI. Now what we will do is that in second step, we are going to find strain, and you know that strain is equal to change in length divided by original length. Let me write original length, L. So change in length or stretch is given as 0.002 inch, 0.002 inch, and original length of this bar is 5 inch. So inch divided by inch, and you will get 0.000400, and it will be inch by inch or unitless because they will cut each other. Now modulus of elasticity E will be equal to stress over strain. So you have both the value. Stress is 11.43 KSI and strain is 0.000400 inch per inch. So you will get the value of modulus of elasticity will be 28.6 into 10 raised to power 3 KSI, which is the answer of our this question. So this is the modulus of elasticity for the given load and the cross-sectional area for the material. And that was all about this problem 3-13. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel further. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 3-23 that is taken from chapter number 3, Mechanical Properties of Materials, that is taken from Mechanics of Material by R.C. Hibbeler. So statement is the stress strain diagram for many metal alloys can be described analytically using Ramberg-Osgood 3-parameter equation, which is this one, where E, K, and N are determined from measurement taken from this diagram. Clear? Using the stress strain diagram shown in the figure, take E is 30 into 10 raised to power 3 KSI, determine the other two parameter K and N, and thereby obtain an analytical expression for the curve. So you can see this is stress strain curve and this is Ramberg-Osgood equation. So you have to find this K and N. Clear? So let's start with the solution. So as per Ramberg-Osgood equation, we have strain is equal to stress divided by modulus of elasticity plus K into stress power N. This is your equation number 1. Clear? Now from stress strain diagram, we will calculate this. We will calculate the stress and strain. So for, you can see here, this is stress, which is 40. So as per this stress, we have strain 0.1. So stress is, if stress is 40 KSI, clear, and your strain is 0.1. Put these values in equation number 1. So what you will get is that strain is 0.1, stress is 40 KSI. So 40 divided by E is 30 into 10 raised to power 3 KSI plus K, which is not known, is sigma is 40 power N. So from here you will get 0.1 is equal to 0.00133 plus k into 40 power n. And if you further simplify it, so 0.1 minus 0.00133 is equal to k into 40 power n. And this will give you 0.09867 is equal to k into 40 power n. That this is your equation number 2. Now again, from stress strain diagram, we will choose another value of stress and strain. So you can see, you can choose this point. You can choose any other one, but these are feasible. So stress is 60 and strain is 0.3. So I will write it, strain is equal to 60 ksi and strain is 0.3. So put it in equation 1 again. So when you put it, you will get 0.3 is equal to 60 divided by E is 30 into 10 raised to power 3 plus k into 60 power n. And if you further simplify it, 0.3 is equal to 0.002 plus k into 60 power n. And we will get 0.3 minus 0.002 is equal to k into 60 power n. And this term will give you 0.298 will be equal to k into 60 power n. This is your equation number 3. Now what we will do is that we will divide equation 2 by equation 3. So this is equation number 2, 0.09867 is equal to k into 40 power n. And we will divide it by equation 2, which is 0.298 divided by k into 60 power n. And you will get 0.3311 kk will cancel each other, clear, and we will left with 40 power n divided by 60 power n. And that will give you 40 divided by 60 power n will be equal to 0.3311 n. From here you will get 0.3311 will be equal to 0.6667 power n. Now what we will do is that take natural logarithm on both sides. So what we will get is ln of 0.3311 will be equal to ln of 0.667 power n. So from here you will get ln of 0.3311 will be equal to n times ln of 0.6667. And we are interested to find n, so n will be equal to ln of 0.3311 divided by ln of 0.6667. So n will be equal to this will give you minus 1.105 divided by minus 0.404. So you will get n will be equal to 2.73. So this is the equation, n is equal to 2.73. Now what we will do is that put n is equal to 2.73 in any equation, either equation 2 or 3. So here I am going to put it in equation 2. So equation 2 is this one. So you will get 0.09867 is equal to k into 40 power 2.73. Okay, and k will be equal to 0.09867 divided by 40 power 2.73. And when you solve it, you will get k will be equal to 4.17 into 10 raised to the power minus 6. Clear? So these are the value of n and k. And if you put it in this equation, so your final Rambert-Osgood equation will become equal to strain is equal to stress over E plus K was 1.4.17 into 10 raised to the power minus 6 into sigma power 2.73, which will be your final equation that is being asked to obtain an analytical expression for the curve, and this equation is valid only for this curve. And that was all about this problem 3-23. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me.